calculation of reacting masses, gas volumes, and mole concentrations. Chemistry Explained are chemistry lessons designed for you to participate in. So make sure that you are writing notes and completing tasks on paper or on tablet. Move through the lesson at the pace that suits you. Skip ahead or move back as you wish. Most importantly, when prompted, pause the lesson, complete the task, but taking your time and thinking the problem through. Resume and check and correct your answers before moving on. A quick review of the mole concept from the earlier lesson on the mole. We measure in chemistry the amount of substance in moles. All calculations of quantity must go through a calculation of a number of moles. If you have been shown some shortcut methods by teachers prior to starting A-level, please forget about them. You must carry out quantity calculations through firstly calculating a number of moles. There are 4 ways at A-level to interpret physical data and convert that to numbers of moles: from mass data, from gas volume data, using the ideal gas equation, and from concentration and volume of solutions. You have to be flexible, respond to the type of data that you are working with or have been supplied with or have obtained from experiment, and to select the correct way of calculating the number of moles. So we'll work our way through calculating numbers of moles from mass data, from gas volume data, using the ideal gas equation, and then from solution data. As an A-level student, you must be absolutely secure in calculating numbers of moles from these 4 types of data. We'll then go on to apply numbers of moles to predicting reacting quantities in a further lesson. So you may recall from the mole lesson that the mass of substance can be converted into numbers of moles, and that is any state, gas, liquid or solid. As long as we have the mass, it can be converted into a number of moles via the equation numbers of moles is small n is equal to the mass of substance divided by the molar mass, that is the mass of 1 mole. Now, of course, that equation can be rearranged to give us 2 different subjects. So rather than numbers of moles, we can make the subject mass of substance or molar mass. Could you pause the lesson and rearrange the equation to give you 2 different subjects, the mass of substance and molar mass? Come back to check the rearrangement. Okay, so rearranging is sometimes a problem at A-level. So for here, what we've done, to obtain mass of substance, we've simply multiplied through by molar mass. So we multiply both sides by molar mass. And you'll see on the right hand side that cancels out. So we're left with mass of substance is equal to molar mass times numbers of moles. So that is how you can argue for a rearrangement. Now, molar mass can also be rearranged to as the subject of the equation. Rearrangement of the first equation, we bring molar mass up to the left and numbers of moles down to the right. So molar mass is mass of substance divided by numbers of moles. You must be fluent and confident in using those 3 rearrangements or those 3 equations. Just to reinforce, here are 5 problems on calculating the numbers of moles from mass data, you may wish to do a couple or all 5. Pause the lesson, do as many as you wish until you are absolutely confident, and then come back and check your answers. Okay, so I'm going to reveal all 5 answers. So here we have, very simple, 2.5 grams of sodium carbonate. So it's the numbers of moles is the mass divided by the molar mass, 2.5 divided by 106. A point to make on B, the numbers of moles of magnesium will be 0.34 grams divided by the relative atomic mass of magnesium. You must use the relative atomic masses as supplied in the OCR data booklet, and those relative atomic masses are presented to you to 1 decimal place. So for magnesium 24.3, and later on here 2 tons of iron. 2 tons of iron are 2 million grams. So 1 million grams is 1 metric ton. So 2 million grams divided by the divided by the molar mass of iron oxide. We're using 55.8 for the relative atomic mass of iron as supplied in the OCR data booklet. In this set of problems, calculate the mass by using one of the rearranged equations. So the subject is the mass of compound. Again, try a couple or all 5 examples. Pause, complete, come back to check your answers. Okay, so assuming you are ready, I'm going to reveal all 5. So here are the answers. Let's just run through one example. Let's do example A. Numbers of moles times molar mass. The mass of 1 mole, 26.5 grams. The fact that ethanol is a liquid, the fact that carbon dioxide is a gas, that sodium carbonate is a solid is irrelevant to the calculation of mass. It's numbers of moles times the molar mass. And now 3 problems on calculating molar mass from data. So ABC, a liquid, a solid and a gas. Can you calculate the molar mass in each case? Pause, complete, come back to check your answers. Okay, so if you're ready, I'm going to reveal all the 3 answers. So the molar mass is the mass of substance divided by the numbers of moles. So that gives us a molar mass for liquid A of 46 grams per mole. Similarly, mass divided by numbers of moles, mass divided by numbers of moles. Moving on to numbers of moles and gas volume data. So we need to recall the idea of the molar gas volume from the lesson The Mole. 1 mole of any gas has a volume of 24 decimeters cubed at room temperature and pressure, and that is called the molar gas volume. It is the same volume regardless of the gas in question. And therefore the volume of any number of moles is simply the numbers of moles times 24 at room temperature and pressure. Pause and rearrange that to make the subject not volume but number of moles. Okay, so I'm going to show you the rearrangement. I've achieved that. I'm going to be pedantic about this because not everyone can do this. I'm going to divide both sides by 24 decimeters cubed. So I'm treating both sides the same. I'm dividing by 24. You'll see on the right hand side the 24 cancels out above and below the line. So we've got volume divided by 24 is equal to number of moles. In the lab, most measurements are in centimeters cubed. Bear in mind that 1 decimeter cubed is 1,000 centimeters cubed. Can you rewrite this equation in centimeters cubed? Pause, rewrite it, check your answer. So 24 decimeters cubed becomes 24,000 centimeters cubed. So you must be sure that you've got the same unit above and below the line when calculating numbers of moles. Three problems. Calculate the volume at room temperature and pressure of the stated numbers of moles of the following gases. 0.12 moles sulfur dioxide, 8 moles of hydrogen bromide, and 0.009 moles of propane. Pause, complete, come back to check. Okay, so here are the correct answers. Numbers of moles, 0.12 times 24. Sulfur dioxide, it's irrelevant, any gas. Numbers of moles, 8 times 24. Hydrogen bromide, the identity of the gas, is irrelevant. Every gas has the same molar gas volume at room temperature and pressure. 0.009 times 24. And of course our unit is dm cubed, decimeters cubed, because we are using 24 as our molar gas volume. So this time, calculate the numbers of moles of the gas from the given volume at RTP. So we've got 1.2 decimeters cubed of sulfur dioxide. How many moles is contained in that volume? Do all three, complete, come back to check your answers. Okay, I'm about to reveal. So volume 1.2 divided by 24, 0.05 moles. Volume divided by 24,000. Why 24,000? I hope it's obvious, because the 25 is in centimeters cubed, so I need to keep the volume, the molar gas volume, in centimeters cubed. So I've used 24,000. 720 in decimeters cubed divided by 24 is 30. 30 moles. Using the ideal gas equation, PV equals nRT. Just as way of introduction, we'll do a little background to the ideal gas equation. We're going to assume that volume is inversely proportional to pressure. That is, if you double pressure, the volume will halve. If you double temperature, the volume will double, all other factors such as numbers of moles and pressures being kept constant. If you double the numbers of moles, then volume would double, other factors held constant, so that again is a proportionality. Volume is proportional to number of moles. Now if we combine those into a proportionality of PV is proportional to NT, so pressure times volume is proportional to the numbers of moles times temperature. If we introduce a gas constant R, then we get rid of the proportional sign and have an equal sign. PV equals nRT. You do not need to know anything about the derivation in OCR Chemistry A, simply that PV equals nRT, where P is pressure, V is volume, N is the numbers of moles, R is the universal gas constant, and T is the temperature. The complexity to the ideal gas equation as far as A-level questioning is concerned is the issue of units. So the units of pressure are pascals. The units of volume are meters cubed. So 1 meters cubed is equal to 1000 decimeters cubed. N is simply a number of moles. Temperature is in Kelvin, which, if you're not familiar, is the Celsius value plus 273. And the universal gas constant has a value 8.31. Making sure that units are correct, so the value is correct for the correct unit before putting them into the ideal gas equation, is crucial if the correct answer is to be achieved. So let's model the solution to a problem. Calculate the numbers of moles of xenon present in a 2 decimeter cube container at 20 degrees Celsius and a pressure of 5 times 10 to the 5 pascals. Now I strongly recommend that you start by writing out PV equals nRT and then rearranging to produce the correct subject, or to highlight the subject of your equation. So N is what we're looking for, calculate the numbers of moles. So N equals PV divided by R times T, so PV over RT. Now, as mentioned on the previous slide, we need to make sure that the units are correct. So the volume was given in decimeters cubed, so to turn decimeters cubed into meters cubed, we divide by 1000. So we have 2 decimeters cubed becoming 0.002 meters cubed. The units of pascals were as per given in the question, so that's not a problem. Kelvin is the Celsius value plus 273, so temperature is 293 Kelvin, and then R remains as a constant, 8.31. So we plug those into our rearranged equation, solve for the numbers of moles. So the numbers of moles of xenon present was 0.41 moles. Now you may also then be asked to calculate the mass of xenon. So then we have to go back into mass is numbers of moles times molar mass. So in this case 0.41 times 131.3, again using the relative atomic mass to 1 decimal place as per the OCR A data table, comes out as 53.93 grams. So 0.41 moles of xenon or 53.93 grams would satisfy those requirements. I'd like you to try a problem of your own. So here is that problem. Calculate the mass of helium required to inflate a balloon of volume 2.05 times 10 to the 8 centimeters cubed, please note, at a pressure of 200, please note, kilopascals and a temperature of 21 degrees Celsius. So the way forward is to firstly calculate the moles of helium as per the model problem. So using PV equals nRT, calculate the moles of helium and then move on to the mass. So pause, complete the task, come back to check. Okay, so I'm going to reveal how I did the problem. Rearrange, get the correct units. Volume was in centimeters cubed, so 2.05 times 10 to the 8. I've slightly misprinted the volume. It should be 2.05 times 10 to the 8. Divided by 1 million gives us 205 meters cubed. Pascals are required, so kilopascals multiplied by 1000 to give us the pascals. 200 times 1000 is 2 times 10 to the 5. Temperature 294 Kelvin. R is the constant. Put those numbers in, solve for N, a large 16,000 odd moles. Then we want the mass of helium. So using mass is moles times molar mass. The molar mass of helium is 4. So the mass of helium would be a little over 67 kilograms, 67,127 grams. Calculating the numbers of moles from solution data. So the idea of concentration is principally the idea of moles, dissolved moles per unit volume. And that brings us to our definition of concentration in this context of numbers of moles divided by volume. That volume must be in decimeters cubed. The units of concentration are moles per decimeter cubed, so the volume must be in decimeters cubed. There are two possible ways of rearranging that equation. I'd like you to pause the lesson and write out the two rearrangements, changing the subject in each case. Come back to check. Okay, so I'm going to reveal. So numbers of moles, we can bring volume up to multiply both sides by volume, gives us concentration times volume and leaves us with numbers of moles. So numbers of moles is concentration times volume. Or we can simply move volume to the left hand side and concentration to the right. So volume is equal to numbers of moles divided by concentration. Please note, volume is always in decimeters cubed. So a few problems. Calculate the mole concentration of the solutions from this given data. So 2 moles of sodium hydroxide dissolved in 0.5 decimeters cubed. Calculate the mole concentration. Do the same for the next 3. Complete. Come back to check. Okay, so having a look at the calculation, it's moles divided by volume for concentration. Moles divided by volume. So 2 is the numbers of moles. The volume is 0.5. Comes out as 4 moles per decimeter cubed. 0.25 moles of sodium hydroxide in 100 centimeters cubed. So 100 centimeters cubed So 100 centimeters cubed is 0.1 decimeters cubed, which explains the 0.1. So 0.25 divided by 0.1 is 2.5 moles per decimeter cubed for our concentration. Now, the next problem, 20 grams of sodium hydroxide dissolved in 2 liters. We need to convert that into moles. So 20 divided by the molar mass, which is 40, comes to 0.5 moles. So that explains that 0.5 on the right hand side, and obviously the volume. The volume is 2, so we come to 0.25 moles per decimeter cubed. On the left hand side here, 4 grams is 4 over 40 is 0.1 moles, and that explains 0.1 divided by 0.25. 250 centimeters cubed is 0.25 decimeters cubed. So mathematics is 0.4 moles per decimeter cubed. So let's have a go at calculating the number of moles given some volumes and concentrations. So 0.5 decimeters cubed at a concentration of 2 moles per decimeter cubed. So we've got a volume and a concentration. We've got a volume and a concentration. Calculate the numbers of moles. Please note in the second example the concentration is given in grams per decimeter cubed, as in the fourth problem. So bear that in mind. Attempt to calculate the numbers of moles present in each situation. Come back to check your answers when you are ready. Okay, so I'm going to reveal. The volume is 0.5 times the concentration. So this is volume times concentration. Numbers of moles is volume times concentration. Comes to 1 mole. 0.25 decimeters cubed. So we have a volume, but we don't have a concentration in moles per decimeter cubed. We have it in grams per decimeter cubed. So we need to know how many moles is 8 grams, so it's 8 over 40 is 0.2 moles. So our concentration is 0.2 moles per decimeter cubed. 8 grams is 8 over 40 moles, so dissolved in solution the concentration is 0.2 moles per decimeter cubed. So our volume times the concentration gives us our number of moles. Over here, third problem, 25 centimeters cubed at 2 moles per decimeter cubed, so no problem with the concentration. The volume though has to be converted to decimeters cubed. So 25 centimeters cubed is 0.025 dm cubed. So that gives us our number of moles. And then finally 200 centimeters cubed of sodium hydroxide, so that's 0.2 decimeters cubed. And we need to calculate, well, 4 grams is 4 over 40, 0.1 moles. So our concentration is 0.1 moles per decimeter cubed. We've got 4 grams in a decimeter cubed. So that's 0.1 moles, so our concentration is 0.1 moles per decimeter cubed times the volume, which is 0.2 decimeters cubed, comes to 0.02 moles per decimeter cubed. And to complete the set, we'll do some volume calculation given a concentration and a numbers of moles of solute. So slightly different presentation. What volume of 0.5 mole per decimeter cubed solution, so that's the concentration of the solution, contains 0.25 moles of solute? So what volume of 0.5 mole per decimeter cubed solution contains 0.25 moles of solute? And similar problems. Pause, complete, come back to check. I'm about to reveal. So we want moles divided by concentration, which will give you the volume. So moles divided by concentration. So the moles, 0.25 moles of solute, doesn't matter what that solute was. And the concentration gives us 0.5 decimeters cubed. Notice the volume is in decimeters cubed. Similarly, what volume of 2 mole per decimeter cubed contains 0.25 moles of solute? So moles divided by concentration will give you volume. The final problem, we need to work out the numbers of moles. 2 grams of sodium hydroxide is 2 divided by 40, that's 0.05 moles. So my numbers of moles are 0.05. Concentration is 0.5, so that comes out as 0.1 decimeter cubed, or 100 centimeters cubed. So for my final slide, just the obvious statement that to consolidate you need to practice, you need to find problems from whatever source you have available to you, but those sources which have comprehensive answers are the best. So attempt the problems, check your answers, move on when you are being consistently accurate and complete in your answers. Choose the next topic that you think for you is the one you need to focus on.